Dude, nature is so awesome. Today I'm going to talk about one of the things that made me want to study nanoengineering. I heard this back in 2011 in my Nanoengineering 101 class at UCSD. I was so mind blown by this that it changed the trajectory of my science career. And today I'm going to share it with you because I think it'll blow your mind the same way it blew mine. This is a Morpho Butterfly. Its color is one of the most brilliant blues you'll ever see in nature. Artists have tried to replicate this color for hundreds of years. Scientists have studied it for decades. But here's the thing. This butterfly has absolutely zero pigment anywhere on its body. None. Not a single blue molecule. So how is it blue? The answer involves nanotechnology, physics of light, and the same engineering principles behind the microchips in your phone. And as a material scientist, it's one of my favorite science topics to talk about. It's one of the reasons why I studied nanoengineering in college. To understand why the Morpho Butterfly looks blue, we first need to talk about how color actually works. What even is color? Like, fundamentally, what are we actually seeing? Visible light is just a tiny slice of the electromagnetic spectrum. That includes radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. All of that is light, just at wavelengths our eyes can't detect. The part our eyes can see is visible light, and it spans wavelengths from 380 nanometers at the ultraviolet end all the way to 700 nanometers at the red end. And every color you've ever seen in your entire life falls somewhere in that range. Violet, blue, green, yellow, orange, red, all just different wavelengths of electromagnetic radiation hitting your retina. So when you see a red apple, you're seeing the wavelength that the apple didn't absorb. The apple absorbed everything else and reflected back the red at you. And the Morpho Butterfly, it's doing something completely different with those wavelengths. Most of the color we see in the world is what's called pigment-based color. A red rose is red because it contains pigment molecules that absorb most wavelength of light but reflect the red wavelength back to your eyes. A yellow banana reflects yellow, green leaves reflect green. The color we perceive is just the light that didn't get absorbed. And this is how most color in nature works. In flowers, in fruits, in human skin, pigment molecules doing chemistry with light. But there's another way to make color, and it has nothing to do with chemistry at all. It's called structural color. And instead of using molecules to absorb light, it uses physical structures. Incredibly tiny, precisely engineered structures to manipulate light at the level of its wavelength. No pigment, no dyes. And the Morpho Butterfly is one of nature's most awesome example of structural color in action. So if we zoom in on that wing, like really zoom in at the nanoscale, you find something pretty interesting. The wing is covered in microscopic scales, like tiny roof shingles overlapping each other. And each of those scales is covered in even tinier structures. Parallel nanostructures running along the length of the scale. And each ridge stacked perfectly on top of each other is called lamellae. Rows of ridges connected by thin horizontal layers stacked on top of each other like a perfectly ordered nanoscale Christmas tree. The whole system together is what material scientists call a photonic crystal, a periodic structure engineered to control how light behaves. And what are these wings made out of? It's a biopolymer called chitin, and it's the same material found in crab shells, lobster exoskeleton, and beetle armor. It's one of the most common biological materials on the planet, and it's completely transparent, but it's the way this material is architected in the Morpho Butterfly that gives it that blue color. These structures are roughly 200 nanometers apart. To give you a sense of scale, a human hair is about 80,000 nanometers wide. We're talking about structures so small, they're comparable to the wavelength of visible light itself. These structures are designed so that when light enters the structure, blue wavelengths constructively interfere and amplify, while other wavelengths destructively interfere and cancel each other out. This is called thin film interference. The geometry of the Morpho's nanostructure is tuned by millions of years of evolution to amplify blue wavelengths specifically. Every other wavelength gets suppressed. The result is this intense, vivid, almost electric blue. And here's the wild part. If you were to crush that wing structure completely flat, the blue would disappear entirely because the color isn't in the chemistry, it's in the architecture. Destroy the structure, destroy the color. This is also why the butterfly looks different depending on the angle that you're looking at it. As the angle changes, the interference pattern changes, and so does the color you perceive. It's the same reason why soap bubbles show different color as it moves. The precision of this is genuinely mind-blowing. Nature built a photonic nanostructure from scratch with no tools, using only evolutionary pressure over tens of millions of years, and it works better than most of what we can manufacture in a lab. Before I started this channel, I spent years working at Intel as a process integration development engineer. My job was essentially figuring out how to build microscopic nanostructures on semiconductor wafers with extreme precision. We're talking about engineering at the scale of atoms. And when I compared it to the science of butterfly wings, I realized that nature is doing nanofabrication. It just has a 60 million year head start on us. Material scientists have been studying structural color for decades, trying to replicate and apply it, and the applications are genuinely everywhere. That shifting holographic image on your credit card or your passport, structural color, that iridescence is almost impossible to replicate without the exact nanostructure, which makes it an incredibly effective security feature. Some high-end cosmetics and nail polishes use synthetic structural color to achieve that deep iridescent shimmer. No pigment, just engineered nanostructures in the formula. The Morpho Butterfly is one of nature's most stunning examples of what has inspired a field called biomimicry, the practice of looking into nature for engineering solutions. Scientists looked at this wing and asked, how can we use engineered materials to replicate this? Nature has had billions of years to run experiments. The solution it arrives at are often more elegant, more efficient, and more durable than anything we've designed from scratch. Spider silk, for example, is stronger than steel at the same weight. The lotus leaf inspired self-cleaning surfaces. Shark skin texture is used in swimsuits and aircraft coatings to reduce drag. And the Morpho Butterfly gave us a masterclass in photonic engineering before we even knew what photonics was. What I love most about this is what it says about science itself. The most profound discoveries aren't made in a lab from scratch. They are made when someone stops and asks, hey, how does that work? A butterfly lands on a flower. Most people see something beautiful, and it is. A material scientist sees a photonic crystal with sub-wavelength periodic nanostructures performing broadband coherent light interference. Both are right, and that's what makes science so cool. So to recap, the Morpho Butterfly has no pigment. Its color comes entirely from nanostructures on its wings that manipulate light through interference. Destroy the structure, destroy the color. And humans have spent decades trying to replicate the same trick in your credit card, in cosmetics, in experimental displays, or chemical sensors. Nature invented nanotechnology. We're just taking notes. Next time you see a blue butterfly, or honestly any iridescent surface, you'll know what's really going on at the nanoscale. Oh, hi, shot. Say hi to everyone. Z, are you my lab assistant? Look at him. All right,